Hello, we're ready for a new Solana update. We have news, we have changes, upcoming changes, proposals, and very nice overview on Solana Consensus by Ryan Chen on the Ilius blog. It's actually very nice to have a place with everything, or at least a good, complete overview on Solana Consensus. So yeah, I definitely recommend to read this article. I'll post a link. But first we talk about changes to the network and to the architecture, and more in particular upcoming changes that we'll see on one of the next releases on Solana Scheduler, and a proposal to introduce exponential fees for write-lock accounts. So let's go. Let's start with the scheduler, but before talking about the scheduler, let's review how transaction execution and ordering works on Solana today. So you have, and that's good to know about how parallel execution works in Solana. So let's have a look. This is a diagram from Umbra Research. Very nice article. Again, always recommend reading whatever they write. So yeah, let's see. On Solana, on your node, you have more execution threads that can work in parallel. And the important thing here is to avoid that conflicting transactions are put in separate execution threads. So here there are conflicting transactions marked in red because they use the same, they want to touch the same state. This state C, this account C that you see here, cannot be processed in parallel. So you have in the execution thread that this transaction that touches A, B, C and was ordered first, this one will be executed, while this one and this one cannot be executed in this round. So you see from this step to this step, you see that the ones that will be executed are only the ones that are not conflicting. And the conflicting transactions will be processed in the next iteration, assuming of course that there are no further conflicts. So next, there is a problem. So first of all, why this is nice in principle is because it enables parallel execution. So you see, you have more threads, you might very well use them. And indeed, here you achieve parallelism in the sense that this transaction can be processed in parallel to this transaction. So that's a way, together with priority fees, to have a first form of localized fee markets. But this doesn't really work as nice as we would like it to be, because it's still cost effective to spam to access highly contested state. So let's say that you really care about touching account C, because it's related to an application for which you can imagine to make profit if you touch it first. So you might just try to spam the network and send many transactions touching this account C, because it's not super reliable to know in which execution thread your transaction will be put. So, you know, there is a difference if your transaction in this pre-execution state is put on this thread, or the other threads. And this is still a little bit random. And also the use of priority fees is not super reliable. It's not like you say, okay, I will pay more priority fees and I'm sure that I will be first in execution. It's still not that obvious. So there are two approaches that can be worked on in parallel. Actually, it's not like either or to make this more reliable. And one is to touch how fees work. And indeed, we will see in the second part the proposal. And the other is to work on the scheduler design. And this is happening. This upgrade will happen soon. So let's see. The difference is that today, like all the transactions that are coming, are assigned again more or less randomly, or anyway there is a random component to, let's say, 4 execution threads here. So the big change with the new scheduler will be to you see, add this other stage here, the scheduler, in between the receiver and the execution threads. This part is not here. So this is the big change. And the point is to have a a pre-assessment of the conflicts between the transaction before putting them on the execution threads. So first you have a better look at what transactions are conflicting, and we'll see how it works. We have this very nice visualization from Harsh Patel, and you can see this is the scheduler. This is the scheduler that is, so these are the transactions that are coming to begin with. And there is this priority graph made by the new scheduler that will basically look already at the conflicts between transactions. So it creates this priority graph to say which transactions are conflicting and which not. And only after this pre-analysis, then the transactions are put in the different threads. This makes everything much more efficient. You don't need as many iterations like before to really process all the transactions. More efficient block space utilization is better because it allows a more reliable use of priority fees, and it's also needed, or anyway it helps for asynchronous block production. There is another big upgrade coming in Solana. So this is good. This is really good, and yeah, can't wait to see it in action. Okay, next, the proposal for exponential fee for write lock accounts. We have seen in the last video, actually, that there was this blog post from Anatoly looking at, presenting how to do this. And now we have this Solana improvement document that goes, talks about the actual implementation of the exponential fee for write lock accounts. I will post a link, and you can see also further discussion among Solana and community developers. So, how does it work? The problem is the same. We discussed the fact that there is still some incentive, or anyway, there is still some space for spam. It's still cost efficient to just spam the network in certain situations. And indeed, almost half of the compute units, CUs in a block, are allocated to failed transactions. These are transactions that they fail because there is a lot of spam, because you are trying to access this highly contested state, and most of the transactions will fail, but you as a spammer will still be profitable. In some cases. It's not always, of course, but in some cases, and we want to remove this inefficiency. So to address this, the proposed feature in this SIMD introduces economic back pressure, discouraging spam activities and ensuring efficient network resource utilization. It suggests tracking the exponential moving average of contentious account CU utilization per block. Okay, so first of all, we have to clarify what this is. So the idea is to track how much or how many CUs are used for every account. So if you're an account that is in very high demand, meaning that and you can track this by the amount how many CUs are touched by this account, are due to this account write locks per block, then you would require higher fees to touch this account. Basically, this is a way to track the demand for each specific account. After you know which accounts are the most in demand, so which part of the state is more contested or anyway needed, then you can exponentially increase the cost to write lock these accounts if their utilization remains high. So what does this mean? This is the actual multidimensional fee market, where every account is a different dimension. So this is the real implementation of localized fee markets, because here you explicitly assign different costs to write lock different accounts. So that's the idea. Of course, in this proposal, you can see more implementation details on how much the fees should increase. And there are implementation details, of course, to be discussed, but the point here is to actually implement these localized fee markets. Next, actionable insights. So from Solana Consensus overview. As I said, there is this very nice article, this very nice overview on Solana Consensus, because we can see everything in the same article, a complete overview of the consensus. And of course, I recommend you to just read the article, but there are some actionable insights explained at the beginning, so let's go through them at least. And the first insight was on the role of proof of history in synchronization. So the point here was to clarify this misconception on the fact that sometimes you might read that proof of history is a consensus mechanism in Solana, or it's a Sybil resistance mechanism, just because it's proof of, like proof of stake. Proof of stake is a Sybil resistance mechanism. But proof of history is not. It's something else. So, it's just good to know, if you're interested in Solana Consensus, to know what is what. Consensus in Solana, you have Tower BFT, and the Sybil resistance mechanism is proof of stake. The point of proof of history is to have this this internal timestamping mechanism. Pretty much that's it, or a way to ensure that all the nodes know have an internal clock that doesn't rely on external protocols for keeping track of time. That's what proof of history is, and it relies on hashing algorithms. They're a little bit like proof of work, in the sense that you have to do these hashes in sequence, and basically this proves the passage of time, because nobody can do this operation faster than a certain time bound, because these are algorithms that are very well known, and they haven't been optimized. We know what is the limit of the hardware, so that's the thing. So it's internal timestamping, it's internal synchronization, and of course this helps with achieving consensus faster. I mean, it removes some inefficiencies with consensus, but it's not a consensus mechanism. Oh yeah. Next, another important thing, vote transactions are necessary for consensus. So you see, when we look at the transactions in Solana, the throughput, it's always important to distinguish between vote transactions and non-vote transactions. Because voting in Solana to participate in consensus is done through actual transactions. And that's nice, because transactions are very efficient, but they're also, the point here is that this helps a lot with consensus. It's very important that all nodes have a good, consistent view of the votes, and this is better guaranteed if the votes are actually transactions rather than messages in a peer-to-peer network. That's the point made here, and it was also said that it's important to note that the transactions are not there, the vote transactions are not there to artificially inflate TPS metrics. And this, if you care a little bit about development in Solana, you know that of course it's not like the team would make some suboptimal decisions that make the network go slower only to inflate the TPS metrics. It would be completely insane, and of course not. But good to remind that that's not the case. So today you have most of this I just took a snapshot in the last 1 hour. Every bar is 1 minute. This is from Solana Compass, and the majority of transactions is vote transactions. But of course, the network here is not at capacity, and with additional demand, you might have non-vote transactions that are more than the vote transactions. And the final insight is that Solana has 2 primary confirmation rules. It's good to know. So you have 2 confirmation rules that are used often, that are mostly used, and one is the confirmed state of a transaction, and the other is the finalized state. So for the confirmed state, you need 66%, at least 66% of the stake approving a transaction, and this can happen in 4 slots. There is 1 block, so 400 milliseconds. But to reach the actually finalized state, for which then you would need to slash a very high amount of stake to the org, so this has higher cryptoeconomic security. This happens after 32 blocks yeah, 32 blocks, so this around 12 seconds. And yeah, it's only at this point that the transaction is finalized, while at this point the transaction is confirmed. And in this plot by Ryan, you can see that the likelihood of transaction inclusion in a canonical block increases monotonically with time, which makes sense. So that is all. This was a fast update this week, and yeah, always happy to present updates. And until next time, I'll see you next. Ciao.